Hello, students. I'm feeling odd today. In fact, so odd, I can't even.
I see what you did there. You read the words.
It's true, I did. Okay, so I'm
Do
looking
you
at
think
the
the people
warm-up.
that write these do you think the people that write these giggle, giggle, giggle as they write these?
Yes, absolutely. They do.
Okay. I'm just
Uh,
curious.
by the way, students, it is not us that write these, although this would certainly be a joke that I would not tell.
He definitely would tell it. Evaluate each expression. Does that mean we plug things in?
It does, and I have a feeling there's a certain reason why we're uh, plugging these specific numbers into these specific problems.
Hmm.
Okay, so I'll do the hard one. I'll do the first one.
Ooh.
And if we've got x to the fourth, I'm going to say this is going to be 2 to the fourth. And I was really careful. I put parentheses around that just to kind of show that we're doing whatever that 2 is first and then raising that to the fourth power. And then 2 times 2 times 2 times 2 is going to be 16.
So can I use your 16, but since I have a negative in front of it, it's going to be negative 16 for that one?
Yes and no. That's not the problem.
No, for number 2.
Yep, that's not to the fourth.
That should be squared. So that should be 4. But same idea. That's
There
that's
you
what
go.
I want to talk about. Okay. Good thing that you know how to pay attention to numbers.
And then looking at the second part of that, let's plug in negative 3 as well. Negative 3 to the fourth. So I'm going to do this one out just to kind of show us what's going on here.
Negative 3 times negative 3 is 9. So I'm going to write that down for me.
I agree. In fact, I've got two different pairs of those 9. So I'm going to do this as 9 times 9.
Oh, that's
Just
81. Oh, I'm so good at this game. So I did number 2 in much the same way. Number 3 will be similar, but you notice how the negative is inside the
I
parentheses.
do notice that.
So, well, I noticed that. I hope they notice that. The negative is inside. And we have to write it like that. And this is saying, okay, what's negative 2 times negative 2, which is 4. So that's 4 plus 1, which is 5. And then the super spicy part is if I put a negative 3 in there, it's negative negative 3 squared plus 1, which is positive 3 squared, which is 9.
Weird. Okay.
So 9 plus 1 is 10.
All right. And then is that x to the eighth that I see?
Yes.
Cool. So 2 to the eighth power. And again, do you notice how we're using parentheses for all of these? Whether or not it's a positive or negative we're plugging in, that's probably a good practice to keep us from messing things up. And 2 to the eighth power, which all of us definitely know just off the top of our heads, is 256.
Oh, I
And,
was going to say 16.
hmm, and Mr. Butterworth is going to do the other part of this.
I love it. So the other part, you put negative 3 and you're raising it to the eighth. So because we're raising a negative 3 and we're doing it 8 times, much like Mr. Carlson did this 3 times, that's going to be the same thing as 3 to the eighth. So it's going to be a positive number.
I like it.
So you didn't want to calculate that, and I just didn't even bother.
Well, could we say that that's like, since 81 is 3 to the fourth, say that this would be like 81 times 81?
Sure.
Not that that really actually helps us.
I mean, we could do it. I just don't want to. Okay. Because they'll get mad at us if we keep spending more time on things.
Oh, look, it moved the page.
Hey.
Okay. So this page is talking about something that happens as we increase the power of our graph more and more. And there are two different patterns that are going on here. So it may be useful to think for a minute before I've got the power. Power.
You were supposed to keep talking.
So it may be useful to think for a minute about what patterns you notice going from x to the first to x to the second to x to the third to x to the fourth to x to the fifth to x to the sixth, and then see if you can like see what's happening for the next two graphs in the sequence.
So here's what I'm noticing. This one, and this one kind of look similar.
I
That
agree.
would be x, x cubed. It didn't catch up, so I was a little scared. And I noticed that I have an arrow going down, an arrow going down, and an arrow going down. So I think my next one's going to have an arrow going down. And then I notice I have an arrow going, nope, not on that one. Arrow going up, and arrow going up. So I'm going to go up. And then if I look carefully, what it looks like it's doing is it's curving, but it looks like it's getting flatter longer
Hey, I wonder
around
if
the
there's a
origin
hint
there.
in the name of this page.
Ooh, it says flat in the middle.
Oh.
That's exciting.
Um,
So I think my next curve is going to look something like that.
that makes sense to me. Um, and just since we seem to be going up by 1 each time, does it make sense that this would be x to the 7?
Yes. And then same idea for the 2, 4, and 6, where we have arrows up, arrows up, arrows up, but it looks like it's getting like in the middle. So maybe something like that, pretending that I actually hit the axis, because I didn't, I'm sorry. So x to the 8th. Hey, there. I missed it on x to the 7th.
Yay! You hit it all along.
So I think I described my patterns as I went.
Okay, so pattern 1, I want to talk about the flat in the middle part. As powers get bigger, get B, that's fun.
Let it be, let it be.
I'm just going to use their language. The middle gets
Is flatter.
flatter. And then we also had a whole bunch of these that were like up on one side, down on the other side, and then some that were up on both sides. And the stuff that's in the middle kind of changed a little bit. It got flatter as we went higher. But I know that there's a relationship between the powers here, where it looks like the red ones that we circled were 1 and then 3 and then 5 and then 7.
Those are
And
odd.
no, you're odd. Oh, you mean the
Oh, no, I'm
number?
Todd. I'm Todd.
Oh, okay. And you know what? That goes to the name of this section, which is so odd. I can't even.
Oh, because the other ones are even. 2, 4, 6, and 8 are even.
So odd powers look something like this. Even powers look something like this. Those
I
are
like
probably
it.
really good things to notice.
Mm. And
Oh,
so
look, more
the first
patterns.
thing I noticed here, like they said the odd and the even thing, but when I looked at the tables, I see for even, all of the stuff here is positive.
Is that because it's got a more positive outlook on life?
No, it's because if you raise the numbers to an even power, you get a positive number.
Hey, we saw that in the war up too.
Right. So like the x to the 8th was positive when we plugged a -3.
Mm-hmm.
Whereas the odd, we go from negative stuff to positive stuff, which matches the graphs that we were talking about, the graphs on the left there.
Yeah, and I was gonna say, like, all of the even graphs look like they've got positive stuff on both ends.
Yeah.
It makes sense based on looking at this table too.
And so, I mean, we could pay attention to these questions. Odd and even degree functions observe the change in values -1 to 1. So for the odd ones, they're opposites, and for the even ones, they're the same.
That makes sense to me.
And then greater or less than, it kind of follows the same pattern. For odd ones, we have like 32 and -32. For even ones, we have the same number, 64 and +64.
And we already talked a little bit about the behavior of the odd on either side of 0, where one side it goes negative, the other side it goes positive. And we talked about the behavior of the even function on either side of 0, where we go from a positive number back to a positive number. Because when we're squaring or quarting, raising to the 4th power,
Quarting.
we end up making those negative input values positive as output values.
And then for number 3, explain why the graphs flatten as the degree increases. So the curves flatten it toward the middle, which is towards 0. And if you think about like the number 1/2 that they have there, if you raise 1/2 to the, what's the highest they go? 5,
Yep.
and then you raise 1/2 to the 6th, not 1/6, 1/2 to the 6th. You notice how those numbers get smaller. So we went, that one's 1/64th, and this one is 1/32nd. So 1/64th is smaller than 1/32nd. And so the higher degree, that was a 6. I messed that whole thing up. I'm sorry. Thank you. The higher the degree, the smaller that number will be. The reason is we're raising 1 to the 6th, which is 1, and then 2 to the 6th, which is a small 64, which is a big number, but we're dividing 1 by a big number. And so the bigger we get, the bigger we get on the bottom, the smaller the overall number gets.
And I think that's the same kind of reasoning for part B here, where the graphs are steepening, where they might start out kind of like this, but if you're making things have a higher power, they're going to go up faster. So it might be more steep on both ends of that and flatter between, which is kind of weird. Okay. So now we're going to look at some symmetry and something called end behavior. And we've already may have talked about this in class. I know that I've used this word in class. I don't know if Mr. Butterworth has, as far as the words end behavior.
I may have. I don't know. I don't listen to myself. The children don't listen to me. I don't know who listens.
So often when we use end behavior as a phrase, we use language that looks really complicated, like this stuff here. And what this is saying, okay, so x, we say approaches infinity.
So that's like x gets really, really huge, right?
Yeah, and like graphically, I think about this as we go to the right. So we're talking
f of x goes to infinity. Does that mean go up?
It does.
Okay. And then obviously the logical connection would be if we go to negative infinity, we're going left for x. And if f of x is going to negative infinity, we're going down.
Exactly. And here we see going to the right and up as this graph moves forward. So this is what this is kind of tying into.
All right, so we're supposed to consider the sequence of graphs shown.
I've considered them.
Okay, what happens to a when the a value is negative, right? Each function in terms of x, and then sketch it.
So we've got some algebra stuff. We got some visual stuff here.
I didn't notice that there were little numbers there. So f1 is x. Negative f1 would be negative x. So the graph would just go whoop.
I agree. F2 is x squared. Negative the whole thing, f2 of x would be negative x squared. And we've talked about this a lot with parabolas, where this is going to be a parabola that goes concave down.
And then negative f3 is negative x cubed. And that's going to take this curve and do something like that. I did my best.
So it flips upside down.
So yeah, in all cases, we're just flipping this thing upside down.
Cool. All right.
What happens when the b value is negative? So f1 was x. So if I plug in negative x, I get negative x. f2 was x squared. So if I do negative x squared, well, that's the same thing as x squared. And then f3 was negative x cubed. So if I do negative x cubed, that's negative x, and negative x. Did I say, sorry, f3 was x cubed, so I plugged in negative x for it. And so these two become x squared. So that's x squared times negative x, which is negative x cubed.
And we already
so that's going to be this idea.
Exactly. I like it.
Now, I don't know that they're going to notice what's going on. But I think how we're going to describe it is An even powered one doesn't change if we change the b value.
Sure.
An odd powered one flips,
That makes sense.
which like I intentionally said flips. I didn't say what it flips over
Yep.
because there is some muddying of the waters there. So we're supposed to complete the table. So if a is greater than 0, so we're supposed to say as x goes to, do I have to write all of that? I don't want to. Can I just write positive, I mean negative, positive?
Or could we draw instead?
That's fine. I didn't know what I was supposed to do there. So
Yeah, I feel like drawing, and I'll erase the middle of this, might be the best option for us in terms of fitting stuff in here.
that makes sense. So an even degree, you're going to be up, up.
So that's like x squared.
Yeah. And then if we make a negative, we flip those things.
So it's like a negative slope
Yeah.
and a negative concavity.
Yes. And my computer had an idea. And we have b is greater than 0. So that's going to be the same thing as a is greater than 0. And then b is less than 0. Odd changes, even doesn't. And we haven't gotten into why and all that stuff, but that's what we're observing so far. Getting rid of those middles. Beautiful. I like it.
Okay.
Now, technically, like if you wanted to write the way they had it, you have as x goes to infinity, y goes, or f of x goes to infinity, blah, blah. These pictures are fine.
So I'm just going to do this one just so that we have that if we need it. As x goes to infinity, that's the right side. Y goes to infinity, although I think they said f of x. So I'll use that notation. And as x goes to negative infinity, that's as we go left. Y is going up there as well. So we say f of x is going to infinity.
Got it. So
Okay.
this one says, if a graph is symmetric about a line, the line divides the graph into 2 identical parts. Is that like the line of symmetry?
Ooh, it's symmetric. Boogie, woogie, woogie.
Special attention is given to the line of symmetry when it is the y-axis, as it tells that the function is even. So that's saying if a function is symmetric about the y-axis, that function is an even function.
That makes sense.
All right, now we got to read what these humans are saying. So we got to decide if we like things or not. Olivia says we have no line of symmetry because if she reflected across the y or x, we would not get a mirror image. Randall says has no line of symmetry because he looks at x values 1 and -1. The y values are not the same, so they can't be symmetry about the y-axis. Also, he looks at y values of 8 and -8. The x values are not the same, so they can't be symmetry. That one's crazy. And then Shedrick said that there is some type of symmetry. He looks at the point 2, 8, notices -2, -8. Ooh, I like this one. And then 1, 1, and notices the point -1, -1 is also on the graph. Must have a reflection across the x and y axis at the same time. Ooh, that's an interesting one.
Okay. So one of the things that I actually really like about all three of these is that their reasoning in all three cases is really good reasoning. Their conclusions are not always correct. And some of that's based on, like, for Olivia, she mentioned specifically the x-axis or the y-axis. Cool. I'm gonna use my finger now.
Okay, your pencil just died. So she just talked about x-axis or y-axis. Well, we could use any other line, right? We could have symmetry somewhere else.
So there are other ways that we can have symmetry besides that.
And we saw that with our quadratics, where we could have an axis of symmetry at x equals 3 or something.
We did. Looking at Randall, it's kind of the same thing, where he's only really considering y-axis symmetry and x-axis symmetry.
Well, he's also only considering, I liked how we assume a he pronoun here. We're assuming that 1 and -1, like very specific x values. And that's a super dangerous game to play. So I wouldn't look at specific numbers there. 1 and -1, 8 and -8. that's a dangerous game to play. Like I like the idea that we are looking at specifically, but you can't use a couple specific examples like that necessarily in our reasoning.
Um, I'm going to disagree with you
Oh, because of the
because
whole
he's
counterexample
saying,
idea?
yeah, he's saying that you can't have these symmetries because these would disprove it.
Mm,
Um, so one of the cool things in math is that it's a lot easier to disprove something than it is to prove that something exists based on using specific examples.
yeah, I think my issue with Randall is he looks at the x values and the y values are not the same. So there can't be symmetry about the y axis. But again, we could have a different line of symmetry. And I think that's what makes me
Right.
uncomfortable is that we're looking at very specific values to claim that we can't have any line of symmetry.
Yeah, I think that's fair. The Shedrick's is interesting, I think.
Yeah.
Um,
I like the nebulous nature where Shedrick didn't like actually commit one way or the other exactly what's going on, but it kind of went with the seems like there's some sort of reflection across both at the same time.
right. And that's kind of a weird thing to think about. Um,
But that is part of the odd nature of things. With the even graphs, they already told us if we're symmetric about the y-axis, then we have the same thing. That's an even graph. With these odd ones, Shedrick's talking about 2, 8, and -2, -8. You notice how you have a point up here and then that same point, but down here. So I kind of agree with the argument, but I don't necessarily agree with the reflection across y-axis and x-axis at the same time.
yeah, it's kind of an awkward way to say that.
Yes.
Okay. Ooh, now here we have a less awkward way to say that. That we're saying this is symmetric about a specific point.
So we don't have to have symmetry across a line. We can have symmetry around a point.
Hmm.
That's
So that seems a
crazy.
little bit different. Um, so thinking again about Shedrick's example where we had 2, 8 and -2, -8. Let's see if this actually works. If I let it charge long enough to get a little bit of juice. Ooh, I did. So if I connect these 2 points, we can see it has to go directly through that origin. And if we were did some Pythagorizing, we could find out how long those pieces were and find that they're exactly the same length. Which, if you remember back to geometry, reflections have to be the same distance from their center on either side.
Oh, that holds for not just reflections about a line, which I learned in geometry, but about a point also.
It does.
Got it. And then that's
Um,
what this is up here is saying kind of their conclusion of what's going on. An even function has a graph symmetric about the y-axis. F of x equals negative f of x. So that means like even function looks like this. You'll notice that if I plug in a negative x, I get the same value as the positive is a way to think about that.
yeah, I really like that. So if this
Whereas
were an example, let's just say x squared, because we know that one pretty well, that we'd have the point 2 comma 4 on the positive side, and we'd have -2, but -2 times itself is also 4.
mm,
So that way we have kind of the algebraic, the numerical, and the graphical all kind of in one page for us. And then the odd stuff, so that's f of x equals negative f of x. I know that odd graphs look something like this. And what this is saying along the same thing is that whatever our x value here and then our y value, whatever we get out from that, if I look at a negative x value, we're going to see the negative y value as well.
so is that like Shedrick's 2, 8 and -2, -8?
It is.
Okay.
And I like that so much, I'm going to include it here.
It's a good thing Shedrick brought that stuff up. All right, now we got Claire. Explain why Claire is correct. So we know Claire is correct. We got the thumbs up. So use function notation to write her conclusion. The reflection of an odd function across the y-axis produces the same graph as its reflection across the x-axis. So the reflection across the y-axis is saying make all positive y values negative y values and vice versa. So negative f of x. And then the reflection across the x-axis, that's when we do things inside. And that's what was going on with that discussion of making b negative. And when I said flip earlier and I didn't specify what we were reflecting across, when we had f of negative x, we're not reflecting across the x-axis, we're reflecting across the y-axis.
And we also know that based on odd functions, f of negative x is the same as negative f of x, which is what we were trying to show it was equal to.
Got it. And I may have flipped those axes in my explanation. I apologize if I did.
I didn't think you did, but you may have.
It's fine. The children won't tell me, so it's fine.
No, it's true.
State whether the graph is each function is even, odd, or neither.
Ooh.
Okay, so we need to look at these graphs, and that one appears to be even for the first one. The reason I picked even is because I looked at several points. It looks like it goes through a little bigger than 1, a little less than -1. Same thing with 2. It's like 2, -8-ish. No, -6-ish, and -2, -6-ish. So it
you're
looks like
saying
the
that
same for all those.
2 points, or any 2 points that are on opposite sides of the y-axis, should have the same height, and they appear to in this graph.
Right. And for B, it's definitely not even. I can tell you that because you just said any 2 points kind of same distance away have to have the same height. That doesn't really hold
Yeah,
for all of the points here. Oh geez, I'm trying to erase and I can't. There we go. Because this is like a half and this is negative a half, and those aren't at the same place.
and like this point at maybe 2.5 doesn't exist over there.
Got it. And then so let's jump to C and then we'll come back to B. So for
Okay.
C, we notice we have, say, this point down here.
I'm going to say this one's not even also.
Yes, it's definitely not even. And this point down here. So definitely not even, but those look like opposites. And then we have a point here and it's kind of opposite point down here. So that one looks odd to me.
It also looks odd to me. It's because it's a strange graph.
That's right. But then the one up here, we don't have the odd thing going on, because if I have, say, 1.5 over here, 1.5 over here is, oh, it's down here. So it's not odd either. So this one's going to be neither or neither. I don't know.
Let's call the whole thing off.
Okay, now we got to do stuff algebraically.
Okay, and just to kind of think about what we had talked about earlier, we had said a whole bunch of stuff like this, like negative x in parentheses squared was the same thing as x squared.
Mm.
We also said negative x to the third power was the same as negative x to the third power. And I think talking about that now is probably helpful for what we're doing here. The other thing I want to remind us of is that something is odd if f of negative x is the same thing as negative f of x. Something is even if f of negative x is the same thing as f of x.
I'm going with what you just said. So I plugged in negative x for where I see x's. And then you told me that negative x cubed was negative x cubed. That would be negative x cubed in parentheses. It's the same thing as negative x cubed without parentheses. And then same thing with negative x. I just plugged that in. So then the first term is negative 2x cubed. And then the second term is plus 3x. So my question is that the opposite of what I started with?
I'm going to say I think so, because if I distribute this negative to both of these pieces, I get negative 2x cubed and plus 3x, which is the same thing we had there.
So that one's got to be odd, because those are opposites.
All right, so for the second one, we've got 6x squared plus 10. I'm going to try plugging negative x in, so g of negative x. And we get 6 times negative x squared, and then plus 10, no x to plug in there. We know negative x squared is the same as thing as x squared, so I'm going to write this as 6x squared plus 10. And by golly, Mr. Butterworth, that looks
That's
like
the
the
same.
same thing.
That must be even.
Even.
I'm gonna hope that they're thinking right now and that they might be able to suggest what the next one's going to be based on structure. But if they can't, I'll explain that structure in a moment. So that first term is going to be negative x cubed. The second term right here is going to be x squared. So that's still in minus 3x squared. And I'm already in trouble. I'm going to keep going. So plus 2x, because negative 2 times x is plus 2x plus 7. And the reason I said I was already in trouble is because you notice how the first term is the opposite and the second term is the same.
Hmm.
I'm in trouble.
Now, if they didn't notice that structurally, would it be okay to say negative and then this whole thing just to check?
Yeah, of course.
We get negative x cubed plus 3x squared. And hopefully we're noticing that same issue we had where some of these are matching up and some are not.
So we're saying that in order to determine if a function is even or odd, everything needs to be consistent. So it's all the same or it's all opposite, not like halvesies in this, which is how this one's going. So this one is neither or neither, or we're writing it at the same time. And the reason I said at the beginning of C, hopefully they're thinking, is because in A, x cubed and x are both odd. In B, x squared is even, and 10 is just a number, so it's not going to change. But in C, we have an odd piece, an even piece, an odd piece, and then a constant. So if you notice that sort of structure, that gives you a hint that maybe we're not going to be odd or even.
I like it.